division lemma.
Two versions of division algorithm. Any positive integer a can be divided by another positive integer b in such a way that it leaves a remainder r and quotient q, where r is smaller than b. So, a is equal to bq plus r. 0 is less than or equal to r less than modulus of b. Many of you probably recognize this as the usual long division process, where a is dividend, b is divisor, q is quotient, r is remainder. For each pair of positive integers a and b, we have found non-negative integers q and r such that a is equal to bq plus r. 0 is less than or equal to r less than b. This division algorithm is known as Euclid's division lemma. A lemma is a proven statement used for proving another statement. Dividend is equal to divisor into quotient plus remainder is Euclid's division lemma. Euclid's division lemma can also be called as Euclid's division algorithm. Some results regarding division algorithm. If b is equal to 2, then 0 is less than or equal to r less than 2. From type 1, we get r equal to 0 or 1. Therefore, a is equal to 2q or a is equal to 2q plus 1. So each integer a is of the form of 2q or 2q plus 1, where q is an integer. If a is equal to 2q, q belongs to z. Then a is divisible by 2 and a is an even integer. If a is equal to 2q plus 1, q belongs to z. Then a is an odd integer. It means even integers and odd integers are in the form of 2k and 2k plus 1, where k belongs to z. Take k is equal to q. If modulus of b is equal to 3, then 0 is less than or equal to r less than 3. It means r is equal to 0 or 1 or 2. Therefore, each integer a is of the form of 3k or 3k plus 1 or 3k plus 2. Take q equals to k, where k belongs to z. Any positive odd integer is of the form 4k plus 1 or 4k plus 3. K belongs to z. If modulus of b is equal to 4, then a is equal to 4k plus r. 0 is less than or equal to r less than 4. So r is equal to 0 or 1 or 2 or 3. If r is equal to 0 or 2, then a is equal to 4k or a is equal to 4k plus 2, which is equal to 2 into bracket 2k plus 1 is even integer. But a is odd integer. Therefore, r is equal to 1 or 3. Therefore, a is equal to 4k plus 1 or a is equal to 4k plus 3. K belongs to z. Therefore, any odd integer is of the form 4k plus 1 or 4k plus 3. In 3k plus 2 equal to 3 into bracket k plus 1 minus 1 is equal to 3k dash minus 1, where k dash is equal to k plus 1. If a is not divisible by 3, then it is of the form 3k plus or minus 1. Example. Use Euclid's division lemma to show that the square of any positive integer is either of the form 3m or 3m plus 1 for some integer m. Solution. Let a be any positive integer and b is equal to 3. So a is equal to 3q plus r for some integer q that is greater than or equal to 0, and r is equal to 0, 1, 2 because r is greater or equal to 0 and less than 3. Therefore, a is equal to 3q or 3q plus 1 or 3q plus 2, or a square is equal to 3q the whole square or 3q plus 1 the whole square or 3q plus 2 the whole square, which is equal to 9q square or 9q square plus 6q plus 1 or 9q square plus 12q plus 4, which is equal to 3 into 3q square or 3 into 3q square plus 2q plus 1 or 3 into 3q square plus 4q plus 1 plus 1, which is equal to 3n1 or 3n2 plus 1 or 3n3 plus 1, where n1, n2 and n3 are some positive integers. Hence, it can be said that the square of any positive integer is either of the form 3m or 3m plus 1. Prove that 6 divides n into n plus 1 into 2n plus 1 for any n belonging to natural numbers. The proof is as given here. If n is equal to 1, then n into n plus 1 into 2n plus 1 is equal to 6. Or, if n is equal to 2, then n into n plus 1 into 2n plus 1 is equal to 30. Both 6 and 30 are divisible by 6. Now, n or n plus 1 is even, they being consecutive integers. Therefore, 2 divides n into n plus 1 into 2n plus 1. Also, n is equal to 3k or 3k plus 1 or 3k plus 2 for some k belonging to natural numbers. If n is equal to 3k, then n into n plus 1 into 2n plus 1 is equal to 3k into 3k plus 1 into 6k plus 1, which is divisible by 3. If n is equal to 3k plus 1, then n into n plus 1 into 2n plus 1 is equal to 3k plus 1 into 3k plus 2 into 6k plus 3. Now, taking 3 common from the third bracket, we get 3 into 3k plus 1 into 3k plus 2 into 2k plus 1, which is divisible by 3. If n is equal to 3k plus 2, then n into n plus 1 into 2n plus 1 is equal to 3k plus 2 into 3k plus 3 into 6k plus 5. Now, taking 3 common from the second bracket, we get 3 into 3k plus 2 into k plus 1 into 6k plus 5, which is divisible by 3. Therefore, in any case, 2 and 3 divide n into n plus 1 into 2n plus 1. Therefore, n into n plus 1 into 2n plus 1 is divisible by 6, as 2 and 3 have no common factor. Euclid's division algorithm is a technique to compute the highest common factor, HCF, of two given positive integers. We know about highest common factor and least common multiple. HCF and LCM are correlated to each other. Highest common factor. If A and B are positive integers and if C divides A and C divides B, we say C is a common divisor of A and B. Since C is less than or equal to A and C is less than or equal to B and the number of positive integers less than A and B both are finite, there must be a largest common divisor or a largest common factor of A and B. This positive integer is called the highest common factor of A and B. So the highest of all the common factors of A and B is called the highest common factor of A and B and is denoted by HCF of A and B. If D is HCF of A and B, then D divides A and D divides B. If C divides A and C, D is the highest common factor of A and B. If C divides A and C divides B, then C divides D. A shop owner has 330 toothpaste and 65 bottles of hair cream. He wants to stack them in such a way that each stack has the same number and they take up the least area of the shop. What is the maximum number of items that can be placed in each stack for this purpose? Solution. Suppose D is number of items in each stack. In each stack, number of items is same. Now, 330 upon D and 65 upon D is the number of stack. This number will give the maximum number of items in each stack and number of stacks will be the least. The area of the shop that is used up will be the least. So D is equal to HCF of 330 and 65. Now 330 is equal to 65 into 5 plus 5. 65 is equal to 5 into 13 plus 0. The last non-zero divisor is 5. Therefore, HCF of 330 and 65 is equal to 5. So the shop owner can make stacks of 5 for both kinds of items. Theorem 1.1. Euclid's division lemma states that given positive integers a and b, there exist unique integers q and r satisfying a is equal to bq plus r, where 0 is less than or equal to r less than b. Suppose a and b are positive integers where a is greater than b. Now, divide a by b and we will get successive divisions as follows. A is equal to bq0 plus r0. R0 is greater or equal to 0 and less than b. B is equal to R0 Q1 plus R1. R1 is greater or equal to 0 and less than R0. R0 is equal to R1 Q2 plus R2. R2 is greater or equal to 0 and less than R1 up to Rn minus 3 is equal to Rn minus 2 Qn minus 1 plus Rn minus 1. Rn minus 1 is greater or equal to 0 and less than Rn minus 2. Repeating this process successively gives smaller numbers until one of them is 0. We get Rn plus 1 is equal to 0. So Rn minus 2 is equal to Rn minus 1 Qn plus Rn, and Rn is greater or equal to 0 and less than Rn minus 1. Rn minus 1 is equal to Rn Qn plus 1. Non-zero remainder Rn is the HCF of A and B. Rn divides Rn minus 1. Rn divides Rn minus 2, and so on, up to Rn divides B. Rn divides A, where D is equal to HCF of A and B. And if D is equal to HCF of A and B, then D divides A, D divides B, D divides R0, D divides R1, D divides Rn minus 2, D divides Rn minus 1, D divides Rn. Therefore, Rn is equal to D. Therefore, HCF of A and B is equal to Rn, which is equal to non-zero remainder. If B is a factor of A, then for positive integer C, A is equal to BC. B is the factor of both A and B is the highest factor of B. Therefore, if B divides A, then HCF of A and B is equal to B. We can find HCF of two positive integers by using Euclid's division algorithm. Let us understand the method of finding HCF of two positive integers A and B, A greater than B, using Euclid's division algorithm. Step 1. By Euclid's algorithm, find Q and R, where A is equal to BQ plus R. R is greater or equal to 0 and less than B. A, B, Q and R are the dividend, divisor, quotient and remainder respectively. Step 2. If R is 0, HCF is B. If R is not equal to 0, apply the algorithm to B and R. Step 3. Continue the process till the remainder is 0. The divisor at this stage is the required HCF. Use Euclid's algorithm to find the HCF of 120 and 23. Solution. 120 is equal to 23 into 5 plus 5. Here, A is equal to 120, B is equal to 23, Q is equal to 5, R is equal to 5. 23 is equal to 5 into 4 plus 3. Here, A is equal to 23, B is equal to 5, Q is equal to 4, R is equal to 3. 5 is equal to 3 into 1 plus 2. Here, A is equal to 5, B is equal to 3, Q is equal to 1, R is equal to 2. 3 is equal to 2 into 1 plus 1. Here, A is equal to 3, B is equal to 2, Q is equal to 1, R is equal to 1. 2 is equal to 1 into 2 plus 0. Here, A is equal to 2, B is equal to 1, Q is equal to 2. R is equal to 0. Therefore, last non-zero divisor is 1. Therefore, HCF of 120 and 23 is equal to 1. Use Euclid's algorithm to find HCF of 420 and 130. Solution: 420 is equal to 130 into 3 plus 30. Here, A is equal to 420, B is equal to 130, Q is equal to 3, R is equal to 30. 130 is equal to 30 into 4 plus 10. Here, A is equal to 130, B is equal to 30, Q is equal to 4, R is equal to 10. 30 is equal to 10 into 3 plus 0. Here, A is equal to 30, B is equal to 10, Q is equal to 3, R is equal to 0. Therefore, last non-zero divisor is 10. Therefore, HCF of 420 and 130 is 10. Use Euclid's algorithm to find HCF of 22,461 and 852. Solution: 22,461 is equal to 852 into 26 plus 309. Here, A is equal to 22,461. B is equal to 852. Q is equal to 26. R is equal to 309. 852 is equal to 309 into 2 plus 234. Here, A is equal to 852. B is equal to 309. Q is equal to 2. R is equal to 234. 309 is equal to 234 into 1 plus 75. Here A is equal to 309. B is equal to 234. Q is equal to 1. R is equal to 75. 234 is equal to 75 into 3 plus 9. Here, A is equal to 234. B is equal to 75. Q is equal to 3. R is equal to 9. 75 is equal to 9 into 8 plus 3. Here A is equal to 75. B is equal to 9. Q is equal to 8. R is equal to 3. 9 is equal to 3 into 3 plus 0. Here A is equal to 9. B is equal to 3. Q is equal to 3. R is equal to 0. Therefore, last non-zero divisor is 3. Therefore, HCF of 22,461 and 852 is 3.